Hi, and welcome back to Discrete Math. You've had a lot of time to think about inductively defined data types, recursive procedures, and how to use these ideas to model all different kinds of systems, from directory trees to family trees to sequences of whatever. Okay? At this point, you should feel comfortable with polymorphic data type, inductive data type definitions, and with the definition of recursive functions that operate on values of these types, particularly by doing case analysis in which you distinguish the kind of argument you're getting of a certain type by the constructor that was used to build it and by the arguments that it was given. We're going to now shift in this class from sort of Unit 1 on basics of expressing functions and data types to the topic of logic. And logic and proof is where we're going. But we're going to start with something that will feel very familiar to you based on what you've done in your previous courses in computer science and based on what we've done in this class up until now. So the topic for today's lecture is Boolean algebra. Now, Boolean algebra is an algebra where you have objects like numbers, except they're not numbers and there's not an infinity of them, there's just two of them. So there's two number-like things that we call true and false. And just as in arithmetic, there's operations, but instead of calling them addition and multiplication and so on and so forth, we call them and or and not and so on and so forth. Okay, so Boolean algebra is an algebra like the algebra of arithmetic, but using different objects and different operations involving those objects. But it's still an algebra. So the idea for Boolean algebra came from none other than Mr. George Boole, who in 1854 published one of the seminal books in sort of human intellectual history. The book was called An Investigation of the Laws of Thought, on which are founded the mathematical theories of logic and probabilities. Now that's a mouthful, but I want to call your particular attention to two words in this title. One is mathematical theories, and the other is logic. Probability we're not going to talk about. That would be better handled in a course on machine learning than in this course in discrete mathematics. But the idea that mathematics and logic go together, that in many ways is due to George Boole. I mean, logic has been pursued since at least the time of the ancient Greeks as systems of sound reasoning, right? So modus ponens in Aristotle's famous syllogistic logic says that if you know that A causes B and that A is present, then you can conclude that B must be present too, right? If whenever it rains, the streets are wet and it's raining, why then the streets must be wet. Okay, so logic up until Boole was pursued as almost a kind of a liberal art, whereas Boole shifted the focus to providing what amounts to mathematical foundations, discrete math foundations for logical reasoning. And that's what Boolean logic really was invented for, to underpin already well understood forms of sound logical reasoning. So in this course, what we're going to see shortly is that Boolean algebra is sort of the algebraic interpretation of propositional logic. So once you understand what we do in this section, you'll understand, 2/3 of propositional logic just right off the bat, because it's pretty much the same thing, but with a different skin, if you want to think of it that way. So Boolean algebra, and I'm going to point to on the slides here, Boolean algebra is an algebra, as I said, of Boolean values. And onto bullet 3, familiar to you from ordinary Boolean expressions in ordinary everyday programming. So as we've discussed here before, in mathematical theories, in algebraic structures, in the semantics of programming languages, we tend to think in terms of expressions and how they're what their constituents are. In Boolean algebra, just like the other formal languages that we've talked about in this class so far, we have literal, variable, and operator expressions, and then we have interpretations for what those expressions mean. So an expression is either a literal, variable, or operator expression in Boolean algebra, and I give you an example in the first sub-bullet of bullet 3. So here we have this expression, and what does it say? True and quantity x or not y. I mean, you can make sense of that immediately if you've ever taken a course in Python or Java. It says it's an expression, true and quantity x or not y. Okay, so to parse this, what do? We look to say, well, what's the main connective here? It's that and, ampersand, ampersand. We understand that in C or C++ or Java to be an and operator, a Boolean operator. The literal term on the left, true, we think of that as meaning the Boolean value true. On the right, we have an expression itself built up out of smaller expressions. The smaller expression on the left is a variable expression x, and we assume that x reduces to or represents or means some Boolean value, either true or false. We have the expression not y, which reduces in our mind to the value of y inverted. So if y evaluates to true, then not y evaluates to false. And if y evaluates to false, then not y evaluates to true. So let's suppose x is true and y is false. Then x or not y evaluates to true or not false. Not false evaluates to true. So true or true evaluates to true. That's the right side on the of the ampersand or and operator. And on the left we have true as well, so the entire expression would evaluate to true. So I've covered here both syntax, how these larger expressions are built up out of smaller literal, variable, and operator expressions, and I've addressed the issue of semantics, that every expression in Boolean algebra is a representation of some Boolean value. You evaluate that expression and you ultimately get either a true or a false, and that's how you evaluate expressions, just as you would evaluate arithmetic expressions using ordinary natural numbers and arithmetic operations instead of Boolean values and Boolean operations. So we see larger expressions are composed from smaller ones here by Boolean operators, and or not. And as we'll see in this lesson, there are a whole bunch of Boolean operators that we can think about other than the three familiar ones that we list here. Yep. So in this lecture, I'm sort of hopping down to the second to the last bullet. We're going to precisely define what we mean by Boolean algebra by implementing it essentially within the logic of the lean prover. And in the next domain, here's what's really interesting. We're going to take Boolean algebra here, a kind of a mathematical abstraction of true and false values and various Boolean operations, and we're going to take propositional logic over here, a symbolic language, and we're going to see that the way to interpret expressions and variables and literals in propositional logic is to interpret them as meaning either true or false. And the connectives that we use to build up larger expressions in propositional logic, why they correspond precisely to Boolean operators like and or and not. So we're going to see that there's essentially what we call an isomorphism, which is equivalence up to kind of a change of skin, if you want to think of it that way. Same system, different look. Boolean algebra is isomorphic to the language of propositional logic, and we use the Boolean algebra as an interpretation of the language of propositional logic, and that's what Boole had in mind. He said that for a given logical language, a given set of logical reasoning principles, we can define a corresponding discrete mathematics. And if we do that, then we can take advantage of the mathematics to automate, for example. I mean, he wasn't thinking about automation, but essentially to mechanize the evaluation, for example, of the truth of expressions in propositional logic just by doing the corresponding Boolean algebra, which is even easier than arithmetic. Okay, so that's what we're up to today. So here we present some new terminology for a concept that you already understand. in this class, and the terminology is that of an algebraic structure. And in the rest of this talk, we're going to essentially present Boolean algebra as an algebraic structure. So an algebraic structure is nothing other than a set of values, a set of operations on values of that kind, and a set of properties of or relations among values of that kind, and properties of, and maybe even relations among, operations on values of that kind. So on this slide, I try to make this sort of, crazy terminology really intuitively clear by relating it to something that we're going to study here and that you already deeply know about, and that's the notion of basic Boolean algebra, of course. So let's look at the set of values, the set of operations, and some of the properties of values or objects and operations in Boolean algebra. As you already know, the set of values in Boolean algebra is simply a set with two elements in it, and we call them true and false. The operations in Boolean algebra include unary operations like not, which takes a Boolean value and returns the opposite Boolean value, binary operations like and or, which each take two Boolean values and return a new Boolean value. It's useful sometimes to define ternary or three-argument operations, and an example of a ternary operation is a very simple form of if-then-else. So you can see that I've listed in lean notation the types of the not, the and the if-then-else notation. And let me say that these are not just lean notations, these really are standard mathematical notations for representing types of operations, types of functions. So think about if-then-else. The type is bool to bool to bool to bool. So this is a function that takes three Boolean arguments and returns a bool. And it's usually defined in the following way, or it is defined in the following way. If the first Boolean argument is true, then return the second Boolean argument, otherwise return the third Boolean argument. So again, it's a very simple form of if-then-else, where the Boolean values that you might return are given by the second and the third argument, and the choice of which one of those to return, the true branch and the false branch, if you will, are given by the first Boolean value. So again, if the first Boolean argument is true, return the second Boolean argument, otherwise return the third Boolean argument. And in any case, you get a final bool value as a result, and so this is a ternary operation, one that takes three Booleans and returns another Boolean value. So that should all be pretty intuitive. At this point, you've studied maybe Python, maybe Java, maybe a little bit of C or C++, some other programming languages perhaps, and they all have these notions of Boolean expressions used within conditionals, if-then-else statements, and as controllers for looping constructs like for and while. And so you've seen plenty of Boolean expressions, expressions that reduce to Boolean values, and expressions that are built up using these sort of operators. Okay, so let's switch to the third part of an algebraic structure, the part that has to do with properties of objects or values and properties of operators or relations in algebraic structures, and here in Boolean algebra. So the first property that I want to talk about is a property of the Boolean value called true. And the way that we say this in sort of standard math English is that true is an identity element for the and operator. Now, what that means is not entirely clear in English, but we can be very, very precise in stating that property by using a kind of mathematical logic notation called predicate logic. So to the right of the first sub-bullet under properties, we have a predicate logic proposition that formalizes that statement that we just made, that true is an identity element for the and operator. So let's read that predicate logic proposition carefully, and then we'll ask, as a proposition, whether or not it's true. Okay? So a reading of it is as follows, that upside down A followed by an argument and a type is read as follows. And I'll just read this particular case before trying to explain the general idea. That upside down A is read as for all or for any or for every. And in different circumstances you might want to use different English words for that. But let's read it now. For any Boolean value B, go ahead and you read it. Just repeat it back. For any Boolean value B, and then there's a comma. And you can pronounce the comma as, it is the case that. Okay, so for any Boolean value B, it is the case that B and true equals B. Now that tent-like operator is just a mathematical infix notation, goes between two arguments, and it corresponds to the AND operation, which you already know. If you were writing this in Java or C++, you might use ampersand, but this is the logical notation in both predicate and propositional logic for the AND operator. So let's read the whole thing then. For every Boolean value B, it is the case that B and true equals B. So what does that mean in plain English? It means you're asserting something that might or might not be true, but it's still a valid assertion, that no matter what Boolean value B has, if you AND that value with true, then you get back to the same value B. And that's what it means for true to be an identity for the AND operator in Boolean algebra. So now the question is, well, as a proposition, is it true or not? And the way that we're going to reason about the truth of propositions in predicate logic is not by trying to evaluate them with some kind of eval function, as we've done or as we will do for Boolean algebra in the rest of this lecture. Instead, when we want to know if a proposition in predicate logic is true, what we need to do is to construct a proof of it. So let's see if we can prove this proposition that true is an identity element for the AND operator. Okay? For every Boolean value B, B and true equals B. Well, how many Boolean values are there? There's only two, right? So we can actually do a proof by case analysis. We'll first consider the case where B is taken to be true, and then we'll see if the part after the comma is true. And then we'll take B to be false, and we'll see if the part after the comma is true. And if it's true in both cases, then it must be true in all cases, because there are only those two cases to consider. So if we can prove that true and true equals true, and we can prove that false and true equals false, those are the two cases where B is first replaced by true on both sides of the equation, and in the second case where B is replaced by false on both sides of the equation after the comma, if we can show that the part after the comma is true for every possible value of B, then we will have proved that this overall proposition is true. For every value B of type bool, B and true equals B. So let's consider the first case. Where B is true, then the equation after the comma is true and true equals true. And by simple Boolean algebra that you already know from Java and C++ and Python, we know that that's true. What about the second case where B is false? Well, false and true equals false. And that's correct. False and true does equal false because conjunction is only true when both arguments are true. So in both cases, the predicate after the comma is true, and so it's true in all cases where B is a Boolean value. And so this predicate logic proposition we can now judge to be true. And indeed it is true. Let's go to the next example. False is an identity for OR. False is an identity element for the OR operator. The formal statement of that is for any Boolean value B, comma, it is the case that B or false equals B. And the OR operator in logic is written as that upside down V rather than as two vertical bars. And the two vertical bars are used because, in the old days people didn't have fancy character sets. They just had typewriters essentially to do computing, so they needed something that they could type on their typewriter, and typewriters don't have logical symbols. So logic uses the upside down or as a name for the or operator. So let's do the case analysis. Suppose first that B is true. True or false equals what? Well, true or false equals true, because an or operator applied to two arguments is false only if both arguments are false. So if either or both arguments are true, then a Boolean expression combining those values using or evaluates to true. Okay, so if B is true, then B or false equals B, because B is true. If B is false, then in fact B or false equals false. And so in both cases, the equation is correct, is true, by simple Boolean algebra that you're already familiar with again. And so we can judge the overall predicate, the overall proposition that for all Boolean values B of type bool, B or false is B. The third example represents not a property of an object, not a property of the value true or a property of the value false. The property that true is an identity for and, the property that false is an identity for or. Rather, we're making a statement here about a property of an operation. We're saying the and operation itself has the property of being commutative. Okay, so that's English for what we can now see and understand very clearly as formalized in this language of mathematical logic, predicate logic. And the statement now says for any two Boolean values, B1 and B2, B1 and B2 equals B2 and B1. In other words, this proposition says that no matter what two Boolean values you combine using and, it doesn't matter which order you combine them in. You can say B1 and B2, you can say B2 and B1, and this proposition says that no matter what Boolean values B1 and B2 are, the results of those operations are always going to be the same. Now, you can do a proof here by the same kind of case analysis, but there are more cases now. First, we consider the case where B1 is true. And then for that single case where we've assumed B1 is true, we now have to look at both cases for B2. So in the first of four cases, we look at B1 being true, B2 being true. We hold B1 constant at true, and now look at the second case where B1 is true and B2 is false. Those are the two cases where B1 is true. Now we look at the two cases where B1 is false. B1 is false and B2 is true. B2 is false and B1 is false and B2 is false. Those are now the four cases we have to consider. And if you go ahead and think about how AND works intuitively based on your experience in Java and Python, you kind of already know or feel or intuitively and implicitly understand that it doesn't matter what order you combine the clauses of an AND in, you'll always get the same answer. So in fact, in this case, we also have a proof in essence that AND is a commutative operator. Not every operator is commutative, right? Think about arithmetic. Is plus commutative? Is A plus B always the same as B plus A for any natural numbers A and B? And the answer clearly is yes. But what about subtraction? For any two natural numbers A and B, is A minus B always the same as B minus A? Well, no, right? 7 minus 3 is not the same as 3 minus 7. Good. So there are operators that don't have this property of being commutative. And a final property that I want to just sort of introduce to you is the property of associativity. And for Boolean values, we assert a proposition that might or might not be true until we have a proof of it, that AND is associative. Okay, and what associative means is when you're combining three objects using an operator twice to combine them, it doesn't matter if you combine the first two to get an answer and then combine that with the third, or if you combine the first with the result of combining the second and the third together. So the formal statement in predicate logic, in mathematical logic, is for any Boolean values B1, B2, and B3, B1 and the quantity B2 and B3 is the same as the quantity B1 and B2, whatever that is, true or false, ANDed together with the value of B3. And in fact, this is also a true proposition, a true statement, and it is the case that AND is therefore an associative operator. So an identity element, you should know that concept, the concept of being commutative. You should now be able to remember what that means. That's sort of, something you're responsible for knowing. And that AND is associative. Question for you, is OR associative? Well, that's a good little exercise to go off and do on your own. Do a case analysis. How many cases are there going to be? Well, there's 2 cases for B1. For each of those cases, there's 2 cases for B2, so there's 4 cases. And for each of those cases, there's 2 cases for B3, so there's going to be a total of 8 cases. So you essentially have to write 8 equations involving true and false values, literal values, and operations, and it's all going to work out. You'll find that you always get the same answer on both sides of the equal sign, no matter what the values of B1, B2, and B3 are. And again, you're constructing a proof here by doing a case analysis on the possible values of B1, B2, and B3. Good. So on to the next slide then. I want to come back to this notion of an algebraic structure and just sort of cement that concept a little bit more firmly in your mind by giving you another example. So the top level bullets here just remind you that the elements of an algebraic structure is a set A, we might call it, of values of some kind. And the technical terminology for this set in an algebra is the carrier set. It's just the set of values in the algebra that you care about. We also have a set of operations involving values of that type and a set of properties of objects or properties of relations involving these objects and operations. So let's go back to the first bullet. An algebraic structure has a carrier set. For example, the Boolean values true and false. That's the carrier set, or the set of values for Boolean algebra. What's the set of values for ordinary arithmetic? Using natural numbers? Why, it's the natural numbers. All right, so think of the natural numbers now as an algebraic structure. You've got a set of values, the natural numbers. You've got a set of operations, including things like natural number successor, that given a natural number gives you the natural number that's one more than it, addition, multiplication, division, quotient, factorial, lots of different operations involving natural numbers that you are already familiar with from elementary school arithmetic and high school algebra and your work here in college. Okay, and we can talk about properties of and relations involving these objects. And so, for example, we just saw that true is an identity for the AND operator in Boolean algebra. But we also have that 1 is the identity element for multiplication in ordinary arithmetic. Why is that true? And how would you state that property formally? For all natural numbers n times 1 equals n. That's true, and that makes 1 an identity element for multiplication. What's the identity element for addition? Good, 0. Now let's talk about properties of another property of natural numbers. We can take any natural number and talk about the property of whether it's even or not. Okay? The property of being even. That's another property of natural numbers. The property of being an identity. How many natural numbers have the property of being an identity for multiplication? Yeah, there's only 1. How many natural numbers have the property of being even? Well, a whole bunch of them. How many natural numbers have the property of being less than 5? 0, 1, 2, 3, 4. There are 5 of them. Right? How many natural numbers have the property of being 6 squared? Well, there's 1, right? 36 has the property of being 6 squared. So this is a very intuitive concept. There's nothing, that seems strange about this. It's largely a matter of terminology, but you want to learn to use and to think in terms of properties of objects and of relations involving objects. What's the difference between a property and a relation? Well, a property pertains to one object, and a relation is like a property of a pair of objects, or a three-tuple of objects, or a four-tuple of objects. So a very intuitive example of a property of a relation involving natural numbers is the less than or equal relation, right? Let's see, how many elements are in the less than or equal relation? Well, how many pairs of elements? Well, what about 0, 0? Let's look at that. Does 0, 0 have the property that the first number in that pair is less than or equal to the second one? Yes. How about the pair 0, 1? Well, yeah, that pair has that property too. 0 is less than 1. How about 0, 2, 0, 3, 0, 4, 0, 5? All those pairs of numbers have the property that the first is less than the second. So a property involving more than one object we generally call a relation. And so what we're defining here is the less than or equal relation, which is a relation on pairs of numbers. So it's a binary relation. All right, what about 1, 0? No, that pair does not have that property because 1 is not less than or equal to 0. How about 1, 1? Well, yes, that does have that property where the first is less than or equal to the second. So does 1, 2, 1, 3, 1, 4, 1, 5. What about 2, 0? No. What about 2, 1? No. What about 2, 2? Yes, the first number is less than or equal to the second. So now if you were to write a 2 by 2 grid of all the natural numbers and write check marks for every pair at the intersection of a row and column, what you would essentially do is fill in the upper diagonal of that square, right? Where everything, well, try it out. You'll get the idea. Okay? One more binary relation on natural numbers that I want to introduce here is the equality relation. You may not have thought of equality as a relation, but it's a very important way to think about equality. It's a property of pairs of numbers, okay, or pairs of values of any type, really. So, wow. So equality is almost like a polymorphic relation. That's interesting, right, in the sense that you can talk about equality of objects of any type. We can talk about equality of Boolean values. We can talk about equality of natural numbers. We can talk about equality of names, of strings. Okay, so equality is a very general relation that can be applied to objects of any type. We'll see that we can make that idea precise as kind of a polymorphic relation. But for now, let's just talk about equality involving natural numbers. Does the pair 0, 0 have the property that the first number is equal to the second? Yes. So that pair 0, 0, you can even think of it as an ordered pair, is an element of the equality relation. What about 0, 1? No. How about 1, 0? No. How about 2, 0? No. 2, 1? No. 2, 2? Yes. Right? So now if you were to draw that 2 by 2 grid with natural numbers across the top and down the row, the equality relation is right there. I'm not sure if I'm drawing it the right way, given that I'm talking to you the right direction, but it's all the pairs on the diagonal in that 2 by 2 grid. All the pairs in which the first element is equal to the second are in the equality relation, and all of the other pairs are not. Another way to say that is that all the elements on the diagonal have the property of being equal, whereas the other pairs do not have the property that the two elements of the pair are equal to each other. Okay, so we can think about ordinary arithmetic as an algebraic structure, natural numbers, standard arithmetic operations, and standard properties and relations involving natural numbers. But now we've also seen that we can think about other kinds of values as participating in or comprising algebraic structures. So the Boolean values, of which there are only two, and the Boolean operators, of which there are many, and properties of Boolean values make up a different algebraic structure. So in computer science, we define these kinds of algebraic structures all the time. I mean, in some sense, yeah, it's ubiquitous. Think about strings. Strings are an algebraic structure. We have values from the empty string to the string A to the string B to the string AA, the string AB, the string BA, the string AAB, and the whole infinite set of strings. We have operations on strings, such as append. That's a binary operation. It takes two strings and glues them together into one new string, the binary operation. We have relations on strings, such as one string being alphabetically less than another string. We call that lexicographic ordering. So does one string come before another in alphabetical or lexicographic order? That's an example of a relation involving strings. So strings, think of as an algebraic structure. Okay, and the idea is, in this class, we can begin to be really precise about these algebraic structures as mathematical objects with a specific set of values, a specific set of operations, and properties that pertain to these objects and these relations. So something that you've seen in this lecture so far is that we can state these ideas in English or Mandarin or whatever language you happen to speak as your native language, and mathematicians generally do communicate in such a natural language with each other. But if we really want to be precise about what we mean, we actually need to use mathematical notations to represent the elements of algebraic structures. For example, we need a way to write down what elements are in a set of objects in an algebraic structure. We need precise ways of writing down, specifying operations on these objects, and we need precise ways of articulating propositions about properties that objects and operations have in algebraic structures. And the language in which we represent these ideas precisely is the language of mathematical logic, typically predicate logic, of which the logic of the lean prover is an extension. Right? It's more general, even more general logic than predicate logic. But we can write predicate logic in lean, and that's where we're headed in this class. Okay. So let's go through this slide then very quickly to think about how, in a language like lean, we will express these ideas in absolutely precise mathematical logic. We can use types to represent sets of objects. So for example, we can define a type bool with two values or two constructors, true and false. We can define the natural numbers as a type. We can define the set of strings as a type. We can define set of people as a type and build a little algebraic structure involving, people and operations on people and properties of people and relations, like one person likes another or doesn't. Okay? We can define functions to represent operations on objects of these types. So in Boolean algebra, the AND operation; in natural number arithmetic, the plus operation; and you get the idea. And there are two different ways that we can represent properties of and or relations involving objects in an algebraic structure. We've already seen that we can write what we call predicate functions that take an object or several objects of a given type and return true or false, depending on whether the given object or objects have a particular property or are in a particular relationship with each other. So for example, we defined a little function that told us whether a pair of people liked each other or not, whether they participate in the likes relation. Okay? Simple idea. So we can use functions in lean, for example, in the mathematical logic of the lean prover, if you want to think about it, not as a funny language called lean, but just as mathematical logic. We can represent properties and relations as Boolean predicate functions that take arguments and compute a Boolean value. But we can also represent properties and relations logically, and now you've seen that in this lecture. So for example, we can state the property of the true value in Boolean algebra, the property that it is an identity element for AND, in logical notation for all Boolean values B and true equals B. That's a very precise mathematical representation of that idea that otherwise we have to kind of express in English, which is subject to all kinds of ambiguities and misunderstandings. So as mathematicians and as computer scientists, it's really vitally important to learn these languages of data type definition, function definition, and also the use of mathematical logical notations to make propositions about objects and properties precise, uh, and even to be able to check that proofs of these propositions are true or not. So this is the wrap-up slide that ends the kind of human part of the presentation here, and now we're going to move on to a formalization of the Boolean algebraic structure in Lean in just a second. But before we do that, let's go through where we've been. We've seen that we can define Boolean algebra as an algebraic structure. We've seen that natural number arithmetic is another familiar algebraic structure. So pause the tape here and just say, what are the three main components of an algebraic structure? A set of values, a collection of operations, a collection of properties involving objects, or relations involving pairs or triples or multiple objects of a given kind. Right, okay, it's on the slide, so that makes that easy. What's coming up, sort of the next big idea after today's lecture, is an introduction to a simple logic called propositional logic. And the cool thing about propositional logic is it's basically identical to Boolean algebra. So if you understand Boolean algebra and Boolean expressions in languages like Java and Python, you basically already know propositional logic, or most of the ideas that are there. Okay? So propositional logic you can really think of as kind of a nice language for Boolean algebra. And what we're going to do is we're going to actually define propositional logic as a language with a syntax and a semantics. And the semantic domain for propositional logic is just Boolean algebra. So every expression in propositional logic will have a true or false meaning as a value in Boolean algebra. And the operations in Boolean algebra, like and or not, are reflected as operators in our propositional logic language. So if we have two propositional logic expressions, we can build a bigger expression by connecting them using the and operator or the or operator. Now, if each of those expressions is interpreted as having a Boolean value, let's say true and false, and if the and operator in propositional logic is interpreted as meaning the and function in Boolean algebra, then we can determine whether a big expression in propositional logic is true or not by determining whether its sub-expressions are true or not, and then applying the Boolean functions that correspond to the connectives used to build up those expressions in propositional logic. Okay, so our first task then is to understand precisely what it looks like to define Boolean algebra formally, and then we'll take Boolean algebra as the semantic domain for propositional logic, which is what we'll define and introduce in the next lecture. Okay, so that's the introduction to the rest of this lecture. So take a break, take a little rest, think about what you've thought, stop the video, and then come back and we'll switch over to the Lean prover, and we'll actually build up a fairly complete specification in the formal logic of the Lean prover of this algebraic structure called Boolean algebra. And you can now intuit that there's probably a similar sort of formalism for defining natural number arithmetic, for defining the mathematics of strings, and for defining the mathematics of innumerable other kinds of objects, where we specify objects by defining a type, where we define operations by specifying functions, and where we then specify functions, either logical, where we then specify properties and relations either computationally as Boolean predicate functions or logically as propositions in some logic, usually, and for our purposes that logic will either be propositional logic or most usually in mathematics the logic called predicate logic, which you've already seen an example of here. Okay, so take a break, pause your video, think about what we've covered, and come back and we'll kick over to the Lean prover and take it from there. Right. Okay, we're back, and we've switched over to our lean environment. Go ahead and take a minute to start up your own lean environment and open up the folder where you've been working, and you should end up seeing something like this. So go ahead and pause the video and open up your VS Code lean programming environment, if you will, and we'll get started. Okay, so here's what we're going to do. We're going to create a new file in the source directory. I just right-clicked on source, new file, and I'm going to give it a name, and we're going to call this file boolean.lean. Okay, I'm going to hit Command or Control S on my computer to save the file and make sure that it's sitting in our file system. And now we can get going. So here our task is to specify, and we use that word as a kind of synonym for to define with mathematical precision. We're going to specify the Boolean algebraic structure, the algebraic structure known as Boolean algebra. So we're going to specify Boolean algebra. Okay, and that has, as you know, several pieces. A set of Boolean values, a collection of operations that operate on values of these types, and we're actually not going to do this today. Formalizations of properties of Boolean values and operators. Okay, so we'll leave that out for now. So let's start with defining the set of Boolean values. And the way that we do this in the constructive logic of the lean proof assistant is with an inductive data definition. So usually we would write something like this: inductive bool type, saying that bool is a new type with some values. And in lean, the bool type is already implemented, and the values of this type are called TT for true. So TT is a value of type bool, and FF is a value of type bool. And that's the definition of the Boolean type in lean. That's it. That's all there is. It's a simple enumerated type where we enumerate the terms, TT and FF in this case, that are to be considered to be of type bool. In this way, we define a set of objects for Boolean algebra. Now you can see I've hovered over the red underscore here, and lean is saying this is not a good object declaration because the environment already has an object named bool. It already has a definition of the type called bool. So I'm just going to go ahead and comment out this definition because I just wanted to show you how we would define it if we didn't already have it. And in fact, you can, if you use #print bool in the lean environment, then it will print out information about the Boolean type. And I'm going to highlight this material here. And it says inductive bool is of type, and it has two constructors, bool.ff and bool.tt. Okay, each being of type bool. And so this is the definition of the Boolean type that you would find in the bool library. And if you actually really want to confirm that, you can right-click on bool and go to definition. And there it is. There's the definition of the Boolean data type right in the middle of the lean type libraries. Okay, you don't want to look at all the rest of this stuff. Some of it's a little bit beyond where we are at this point, but trust me, I've given you the correct definition of the bool type. So that's all there is to it. Simple. Okay, so we're done with defining the set, the carrier set of values of type bool. And now we need to look at defining operations on values of type bool. So I'd like to start by thinking about the question, well, you know, what are the types of such functions? And so let's say we're going to define operations here, and we're going to define operations of Boolean algebra as functions in lean. And let's think about what are the types of these functions. Well, we have unary operations, okay, and those will take a Boolean value and return a Boolean result. So not is a good example of a unary operator. Takes one Boolean value and returns a Boolean value, namely the other Boolean value. So if given false as an argument, it returns true, and if given true as an argument, it returns false. We have binary operations, like and, for example, and or. And there are others, NAND, NOR, XOR, implies, equivalent. And we'll meet those other operations that are maybe a little bit less familiar, but they all have the same type. They all take two Boolean arguments and return a Boolean value as a result. So they are of type bool to bool to bool. Take two bools, consume two bools, and reduce to a bool at the end of the day. We saw that there are, or that we can define ternary operations on Boolean values, and these are of type bool to bool to bool. They take three values of type bool and return another bool at the end of the day. Okay, so we have essentially, we could say these are unary operations or one-ary. All right, we have binary operations or two-ary. We have ternary operations or three-ary operations, and we can keep going up if we want. An interesting question is, what if we go down? So we have Boolean operations that take three arguments, two arguments. So the three argument is bool to bool to bool to bool. The two argument operations are of type bool to bool to bool. The unary operations are of type bool to bool. Do we have actually sort of zero-ary operations? And if so, what would be their type? Yeah, just bool. Okay, an operation that takes no arguments is simply a constant. So a zero-ary operation is just a constant of a given type, in this case of bool. So you can really think of values or of data as being kind of degenerate operations, right? They're the lowest form of function, namely a function that takes no arguments and just returns a value. Awesome. Okay, so that's pretty cool. So I'll put an etc. after this, because you can see clearly that you could define 5-ary and 6-ary and 10-ary and a million-ary Boolean functions. And in reality, in real software engineering and computer science practice, we often do end up with Boolean functions with hundreds of thousands or millions or tens of millions of arguments. And we'll see a little bit of that in this course. Turns out this is a phenomenally rich and still very productive area of research in computer science, using Boolean functions in really interesting ways to get stuff done. Okay, cool. So the next question that I want to answer, we answered what are the different types of Boolean functions, Boolean operations, if you want to call them that, implemented as functions. The next question I want to ask and answer is, how many functions are there of each of these types? Okay, and I'm going to build a little table here. Okay, so we have the arity of our functions, 0, 1, 2, 3, which is the number of arguments that a function takes or an operation takes. And we have the number of functions of that arity. So when the arity is 0, when we're talking about functions that take no arguments, in other words, constants, how many constants are there of type bool? And the answer, of course, is that there's just two. True and false. Okay. So we can actually enumerate all of the constants, and we could do it like this. We'll say def. Let's just say const 1 is TT. and const 0 equals ff. And you probably already know that in some languages, 1 is interpreted as, if interpreted as a Boolean value, is interpreted as true. And 0, if interpreted as the number 0, if interpreted as a Boolean value in a conditional, for example, generally is understood to represent false. In fact, usually 0 is false and any non-zero number is taken to be true, but that's beyond relevance here. Okay, so if the arity of a function is 0, then there are 2 Boolean functions of that arity. Okay, so these are 0 array functions, Boolean functions, aka constants. How many Boolean functions are there of type bool to bool? These are the unary or one-ary functions of type bool to bool. Okay. Well, let's be a little bit more careful here, and we'll just put explicit type declarations here just to make it absolutely clear what the types of const 1 and const 0 are. Okay. Cool. So the type of such a function will be bool to bool, take a bool, return a bool. And what does such a function actually look like? Well, what I'd like to do is I'd like to write a little kind of template that we can fill in as we go. So I want to write some templates. So for the first template, I'm going to define a unop as a type, and it's just the type bool to bool. Okay, so this is simply the type of unary operators. What's the type of zero-ary operators? I'll just call it zerob. Well, that's just bool. Okay, good. In fact, while we're at it, why don't you take a second and write the type of binary operators. Good. Bool to bool to bool. And ternary operators, and then we'll stop. And that, of course, is a type of function that takes 3 bools and returns a bool at the end of the day. Just like that. There. Okay. So, let's move these templates just up above where we are. So here are our function templates, operation templates for the different arities of operations that we're going to be looking at. Great. Okay. And in fact, we don't need to have that stuff in comments. That's just real valid definitions in Lean. Just giving names to certain types. The name 0p to bool, the name unop to bool, the name binop to bool, and the name turnop to the type bool to bool to bool to bool. Okay. Here, we're defining constants. Actually, instead of 0p, let's just call this const op. Okay, so instead of bool here, we could write const op, and it would mean the same thing. Good. For the rest of the lecture, I'll just use these types explicitly rather than using these names. I just wanted to give you names for functions so that we can really, for function types, so that we can really see how the types of these functions relate to each other in terms of just taking more and more Boolean arguments, but always returning a Boolean result. Okay, so here are our constant Boolean functions. Now we're on to our unary Boolean functions. And what does a unary Boolean function look like? Well, let's see. A unary function is going to look like this. So I'm going to define unary template of type bool to bool as a function. Okay, we're going to define the function by cases. So the function is going to have two cases, true, in which case we return one answer, and false, in which case we return one answer. Okay, so take just a minute and make sure that this makes sense to you. This is essentially a template where we're going to fill in those placeholders, those underscores, with different Boolean values to define different Boolean functions, different unary Boolean functions. And then we're going to fill those in different ways systematically to enumerate all of the unary Boolean functions so that we can answer the question, how many are there? Okay. So that's what the template looks like. And I'm just going to instantiate this template as many times as I need to fill in all the Boolean functions. So I'm going to call this unary op1. Actually, I'll call this, we'll give it a name in a second. How many ways can we fill in this first value? Well, this is a function, unary op, that takes a Boolean, returns a Boolean. We define the function by case analysis on the first argument, the first and only argument. The first argument is either true or it's false. And in either case, we need to define what the return value is for the function. So one possible way to define the return values for this first function is to say the function always returns true no matter what. Okay. So now I'm going to convert these return answers and comments into zeros and ones, because that's going to give us some real insight into how to think about the number of functions that there are of a particular type. So once again, I'm going to write a 1 for a TT return value. So we have 1, 1 here. So that's our first unary operation. And if we read this number 1, 1 in binary, okay, we could write it as follows, 1, 1. In binary, what does that mean? Well, that's 1 times 2 to the 0th power. 2 to the 0th power is 1. So this is 1 times 1 plus 1 times 2 to the first power. 2 to the first power is 2. So this is 1 times 2 plus 1 times 1, which is 2 plus 1, which is 3. Okay. So in decimal notation, that's 3. Okay. So I'm going to call this unary op3 for that reason. Okay. So now let's instantiate our template again and find a way to define a slightly different function. And again, let's see, I will call this unary op something at the end of the day, and we'll fill in what that number is there when we're done. So look, I want to fill in the two return values in a different pattern so as to define a different function. Let's keep the first one as true, but make the second one false. Okay, so there are two cases, two cases, and for each case we have to return a value. So we have two different ways of returning we have two different values to return. Here's one way to return those two values, both as true. Here's another way to return both of those values, one is true and one is false. And if I convert those return values into digits, binary digits, I have 1 and 0. Okay, 1 and 0 in binary represents 1 times 2 to the first plus 0 times 2 to the 0th, which is 2 plus 0, which is just 2. So we have 1, 0 in binary, and that is equal to 2 in decimal. So we'll call this unop2. Okay? We are just systematically enumerating all of the unary functions of type bool to bool. Now, a third way to fill in these two return values, we've kind of run out of ways to fill in the second value if the first value is true. So let's make the first value false, and now we'll fill in the second value systematically, starting with trues. Okay, so here now we have 0 and 1 as our numerical equivalents of the Boolean return values. If we look at that numeral 0, 1 in binary, that just translates to 1. Aha. Okay, so we'll call this unary op1. And finally, you can pretty much guess what the last one's going to be. Why don't you pause the video, fill it in for yourself, and then I will do it for you. Right. The first case returns false and the second case returns false. If we think about those as binary digits rather than Boolean values, then we have 0, 0, and that is 0 in binary, so we'll call this unary op0. There are no other ways to fill in the two different Boolean return values than the 4 that we've given here. Make sure that you understand that. There's just no other way. We have 2 values to return. We've looked at all possible cases. The first value is true, and the second value is true and false. The second value is false. The first value is true, false. There are no other Boolean values. So these are the only ways that we can fill in those 2 return values in our template in order to instantiate different unary Boolean functions. So let's go put the next entry in our table here. If the arity of our Boolean function is 1, then the number of functions of that kind, the number of unary Boolean functions, is 4. Okay. In fact, let's add a middle column here. And this column is going to be number of cases. And we'll also have number of functions. Okay. So if the arity of our function is 0, there's only how many ways to return a single Boolean value? With no arguments, there's 2. So there's 2 cases. Sorry, this number of placeholders, let's think of it that way. The number of placeholders, if we're talking Boolean unary function, sorry, forgive me. There's one placeholder, okay? So let me be clear about why. What does the template look like? Const will define const template. There. We define const template to be of type bool, and the question is, there's one placeholder to fill in. How many different ways can we fill that in? 2. Here's one way, here's the other way. Okay? Good. So the arity is 0, the number of placeholders is 1, the number of functions is 2, if we're talking about constants. If the arity is 1, that looks like this. We take one bool and return one bool. Then there's 2 cases for the first bool. Okay? There's 2 cases to consider, so there's 2 placeholders to fill in. Okay? And we can fill those in 4 different ways. So there's 2 placeholders, and actually I am going to change this to number of cases, because that's the number of lines in the case analysis that we use to define the function, the number of different lines there are with a return value at the end. Good. Now, do you want to guess how many cases there are? This should be easy. For a binary function, one that takes two Boolean arguments, how many different possible combinations of two Boolean arguments are there? Okay. And how many functions are there that take two Boolean arguments? So let's, we've done our constant Boolean functions. We're doing our unary Boolean functions. Now we're going to go down and build a template. Let's build a template for binary Boolean functions. So now here we are down at the bottom, and we're going to look at binary Boolean functions. Awesome. Let's do a binary template, a template for binary Boolean functions. And a binary Boolean function is going to be of type bool to bool to bool. Let's type it out. Okay. But now we're going to have two arguments to each such function. Okay. And one return value. So the first thing we need to do is to figure out how many cases there are on the left so that we can then decide how to fill in return values for each of those cases on the right. And we just saw that if we have two Boolean slots to fill in, there's 4 ways to do it. And these are true, true, and true, true. Okay, good. The next case would be that the two argument values are true and false. The next case would be that the two argument values are false and true. And the final case would be that the two argument values are false and false. Okay, so for a binary function, we have 4 cases to consider. That means we have to define 4 different Boolean return values. How many different ways can we combine 4 Boolean values? How many different ways can we fill in 4 variables, if you will, those 4 underscores with different combinations of Boolean values? We can fill in the first one in 2 ways. For each of the ways we fill in the first, we can fill in the second in 2 ways, so that's 4. For each of those 4, we can fill in the third one in 2 different ways, making 8. And for each of those 8, we can fill in the fourth one in 2 different ways, making 16 possible ways of filling in the return values. That's pretty interesting, right? This is starting to look like a real pattern, and I'm now going to ask you to think about this. If the arity is some natural number n, then what is the number of cases we have to consider? And what is the number of functions of that kind? So looking at this pattern here, 0 relates to 1, 1 goes to 2, 2 goes to 4. Let's do one more. Suppose that we're talking about ternary functions, which have 3 arguments. Well, if we only have 2 arguments, there's 4 cases, right? With 3 arguments, there's going to be 8 cases we have to consider. Each of the 4 preceding cases for the third argument being true, and the same preceding 4 cases for the third argument being false. That doubles the number of cases that we have to consider. So the number of cases here is going to be 8. And now the question over here is, what's the answer here? Well, if there are 8 cases, then the template is going to have 8 blanks for the 8 cases. And now the question is, how many different ways can we fill in those 8 placeholders with Boolean values? Well, the first one we can fill in 2 ways. The second one we can fill in 2 ways, so there's 4. Then there's 8. Then there's 16 if there's 4 cases, but now there's 8 cases. 32 if there's 5 cases, 64 if there's 6 cases, 128 if there's 7 cases, and 256 if there's 8 cases. This is so cool, right? So we can see that we can actually enumerate all of the functions, all of the Boolean functions of different arities in a very systematic way. Okay, so let's go down and look at, get a start at least on the binary functions, the binary Boolean operators, the functions that take 2 Boolean arguments. Here's our template. There are 2 Boolean arguments. The first one can be true or false, and for each of those, the second one can be true or false, true or false. So there's 4 cases to consider if there are 2 arguments. And therefore, to define a binary function, we simply have to fill in the return values in one way or another. And each of the different ways we can fill in these 4 return values defines a different Boolean function. So let's go ahead and do the first 2. So I will call my first function binary op. I'll call it bin op, okay, just so I don't have to type so much. And we'll put a number there. Of course, this function is of type bool to bool to bool to bool. And what we'll do is we'll simply fill in all trues. We'll let the first one be true, the second one be true, the third one be true, and the fourth one be true. Okay, there you go. Okay, once again, we can relate this set of choices to digits, binary digits, 0 and 1. So that would be, 1. We have 1 here, we have 1 here, and we have 1 here. Okay, and if we read down, essentially we could think of this as being the 1, 1, 1, 1 function in binary. That's 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 1 times 2 to the 3. It's just like base 10 notation, except it's base 2. So that's 1 plus 2 plus 4. 1 and 2 is 3 and 4 is 7 plus 8. That's 15 in decimal notation. Okay, that's 15. Awesome. So we'll call this bin op 15. And it's the operation that takes 2 Boolean values and always returns true. It's simple as that. It's very simple. Okay. So bin op 14, we will change the last one. We'll change, the last one here from true to false. So now we have a 0 here. We have a 0 here. And that is 1 less than 15, which is 14. And so we could call this bin op 14. Okay. I'm going to ask you to go ahead in your homework here and complete the list. Enumerate, well, how many are there? There are 15. Enumerate all 15 binary functions. Now, let's look at the ternary one that we've talked about previously. The ternary function that we've talked about is, and we only looked at one of them, it's the if-then-else function. All right, so let's see what that looks like. We need a template for ternary functions. And it's going to look like this. The function is of type bool to bool to bool to bool. So now we have 8 cases. So the first case could have the new argument be true in all cases, or the new third argument could be false in all 4 cases. And those are the only cases that are there. And this is why there are 8 cases to consider when defining a ternary function. And so now there are 8 placeholders to fill in. So let's fill them in a way that implements the Boolean if-then-else operation. So if the first argument is true, we return the second argument. True, we return the second argument. Otherwise, we return, if the first argument is true, we return the second argument, which is FF here. If the first argument is true, we return the second argument. Otherwise, if the first argument is false, we return the third argument. First argument is false, we return the third argument. First argument is false, we return the third argument. First argument is false, we return the third argument. And there you have it. So this is no longer a template. This is the ternary, let's actually just call it Boole if then else. I'll call it ITE for if then else. Okay, and so this is one of how many different possible functions of this type. The Boolean if then else function is a ternary Boolean operator that has a specific behavior. If the first argument is true, it returns the second argument, otherwise it returns the third argument. And so there you have it. There's a ternary Boolean function, but it's one of many. It's one of how many? It's one of 256 ternary Boolean functions, because there are 256 different ways that you can fill in 8 binary digits, or 8 Boolean values. In the olden days, computers used 8-bit words, where each bit is a binary digit, or you think of it as a Boolean value if you want to think logically. How big a number can you represent in 8 bits? Well, in 1 bit, you can represent 2 numbers. In 2 bits, you can represent 4, 8, 16, 32, 64, 128, 256. You can represent 256 numbers, typically enumerated as 0 up to 255, or 255 down to 0. And, you know, that's how computers worked in the olden days. You could represent numbers in a single word of your computer, a single 8-bit word, numbers from 0 to 255. Or you could make about half of that range represent negative numbers and half of the range represent positive numbers. And in C and C++, you know, this kind of data type is still around, and we call it a short int, an 8-bit integer value. So that gives us essentially a way to see how we can systematically enumerate all of the Boolean operations of any given arity, from constant, which are functions that take 0 arguments and thus can be only one of the 2 possible constant values of a type, to unary, which take 1 argument, 2 possible cases. Each case has to have a return value, 2 return values, 4 different ways of filling them in, so there's 4 functions. Binary, 2 input arguments, 4 ways of combining them, 4 cases. To define a function, you have to fill in 4 Boolean values. There are how many ways you can do that? 2, 4, 6, 8. So there are 8. Wait. Wrong. There are 4 Boolean values to fill in, 2, 4, 8, 16. 16 different ways to fill them in. For ternary functions, there are 8 cases, 256 ways, different patterns of return values if you want to think about it. So we can systematically enumerate all the Boolean operations of any given array. And now the last thing I want to do is the last 2 things that I want to do is I want to come back and look at these operations. So let's start with the unary operations, of which there are these 4. Let's think about them. I've said before that the not operation in Boolean logic is an operation that takes a Boolean value and returns its opposite. So here's a question. Which one of these operations does that? And we're going to actually give it a new name to reflect the fact that it's actually Boolean negation or not operator. Well, this first function, unary op3, returns true no matter what, so that's not it. This Boolean operation, if given true, returns true, if given false, returns false. Well, that looks like an identity operation. So that's interesting. We could maybe call this BID for Boolean identity function. How about this function? If you give it true, it returns false. If you give it false, it returns true. Oh, that's our Boolean negation or not operator. So we could call that B not. Now there's an error here because there's already a function in Lean in the Boolean algebra library called B naught, so we'll just call it B naught with a prime mark like that to not have a name conflict here. And finally, this function down here, given true returns false and given false returns false. So in some sense, this very first function is a binary operator that returns always true. So why don't we call this B true? Okay, it's a unary function, takes a bool, but always returns true. So we'll call it B true. This one down here takes any Boolean value and always returns false, so we'll call this B false. So there you go. Look, we have names for these functions now. The binary operator that takes a Boolean value always returns true. The binary operator that takes a Boolean value and always returns the same Boolean value, call that the identity function on Boolean values. Take a value, just return it straight away without changing it. That's called an identity function. B naught is the function that takes a Boolean value and returns its opposite, no matter which Boolean value you're given as an argument. And B false is like a constant function, but it takes one argument, ignores it, and just always returns false. Okay. Cool. Now, using underscores and such, you could actually probably write these functions in a slightly more compact way, but this is beautiful. Okay, it's very clear, very explicit what's going on. Now, let's see if any of these functions here, if we can give any of these functions interesting names. So I've only listed 2 of the Boolean functions, so I'm going to copy and paste them here. Let's look at this first one, binop15. No matter what combination of Boolean values you give it, it always returns true. So I suppose we could call this, I don't know, B2 true. It's a binary operator, it's a Boolean operation, takes 2 Boolean values and always returns true. Okay, good. Now how about this one? Let's look at what Boolean operation this is. Now, and what I'd like you to do is I'd like you to stop the video right here and study this carefully and tell me what familiar Boolean operation does this function implement? Okay, you've probably already seen it, but if not, let's go through it. If both arguments are true, you get true. If the first is true and the second is false, you get true. If the first is false and the second is true, you get true. And you only get false if both arguments are false. Which familiar Boolean operation is this? And it's very clear that this is the Boolean OR operation, which is already defined in Lean, so we can use a tick mark after the name so we don't get a name conflict. There's your Boolean OR function. Okay. Here's an interesting question. What's the enumerated, what's the index, the number, if we think of this as function 15, function 14, what's the number of the function that implements AND? Well, let's just make a copy of this and modify it to implement the AND function. So we're going to define B AND, and I'll leave a tick mark after the name. I don't know what this number is yet, but let's go ahead and make this the AND function. So clearly, true and true is true. Otherwise, the answer is false. Okay, because the AND function is true only if both arguments are true. Otherwise, it's false. So if we sort of computed an index number for this function, this is 1, 0, 0, 0, 1, 0, 0, 0. That's 0 times 2 to the first, 0 times 1, 0 times 2, 0 times 4, and 1 times 8. So in some sense, binary Boolean function number 8, if you will, implements the AND operation. That is pretty cool. In effect, all Boolean functions, Boolean binary functions, are just variants of this template. And all of the familiar functions familiar binary functions are in this list. Let's talk about a few other binary Boolean functions. How about NAND, the not AND function? The NAND function is just like AND, but it returns the opposite value. So if AND returns true for a given combination, then NAND returns false for that combination of input values. Pause the video and go ahead and define the NAND operation in just the way that we've defined the BAND and BOR operations. And come on back after you start the video up, and I'll go through it myself. Okay, welcome back. Let's take our BAND function definition and just change all of the return values. So we'll call this NAND, and the Lean libraries don't actually provide you with this operation, but you now see how easy it is to do it yourself. And what we have to do is wherever AND returns true, NAND returns false, and wherever AND returns false, NAND returns true. Awesome. So this is 0, 1, 1, 1. So in our indexing scheme, this is the 0, 1, 1, 1 function, and you should now be able to figure out that that's function number 7 in our enumeration, our indexed enumeration, where we assign an index number to each Boolean function based on the pattern of its return values. Okay, that's the NAND function. Okay. I bet that you can define the NOR function yourself. And there are a couple other Boolean functions that are really, 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 really important, binary Boolean functions. One, which you can think of as implementing a kind of equality predicate function for Boolean values, returns true if both arguments are the same, and otherwise it returns false. So if the two input arguments are true, both true, then you get true back. If they're both false, you get true back. Otherwise, you get false. So that's called equiv for equivalence, or you can even just think of it as equality for bools. So let's define let's go ahead and do this one on our own. Okay, we're going to take let's take our template just to be kind of fun about it. Okay, there you go, and we're going to define. Let's call it the equiv. Are the argument values equivalent? Are they equal to each other? Okay. If both argument values are true, then we return true because the arguments are equivalent. If both input values or both argument values are false, we return true because the input arguments are equivalent to each other. But if we get either true and false as arguments or false and true as arguments, we return false because those values are not equivalent to each other. There you go. Okay, so here we could write this as a 1, this would be a 0, this would be a 0, and this would be a 1. Okay, so we have this pattern 1, 0, 0, 1, which is 1 plus 0 plus 0 plus 8. 8, 1, 8, no 4s, no 2s, 1, 1, 9. So index function with index number 9, if you want to think of it that way, is the Boolean equivalence function. Now the last one that I want to cover here is an extremely important one, and it's the one I guarantee will give you the most trouble understanding how to think about what it's really saying. And this is what we'll call the implies function. It's also I'll call it bimpl for implies. Okay, this is a binary function, bool to bool, of type bool to bool to bool. And here's the way to think about it. You can think about, I want to think about it in terms of a constraint on the return values. Okay, and here's the constraint. If the first value is true, the second must be true. And that's it. That's the only constraint. So now when we look at pairs of input values, in the first case, the first one is true, and the second one is true. So that pair of values satisfies this constraint. The first value is true, so the second one must be true as well, and it is. So we return true to indicate that that constraint is satisfied. So we have a 1 here. Now let's look at the second pair of arguments. Does it satisfy this constraint? Yes or no? True or false? It satisfies this constraint. If the first value is true, and it is, then the second value must be true, but it's not. So in this case, we need to return false because the constraint is violated. Now let's look at the third case. The first argument is false. If the first value is true, well, it's not. And so there's no constraint that says the second one must be true. So the second one can be anything, and the constraint is still satisfied. Stop the video, rewind it, listen to that 25 different times, repeat it, repeat it, repeat it until you understand what I'm saying here. It will save you a lot of intellectual effort as we go forward. If the first value is true, then the second one must be, otherwise anything goes. Okay? If the first value is true, the second one must be. That's the constraint that this function checks to see if it's satisfied by its input values. Think of it as a predicate function. It tells you whether or not the two input values satisfy that constraint. If the first one is true, the second one must be. In the first case, the first is true and the second is true, so it satisfies that constraint. In the second case, the first one is true, but the second one is not. So that violates that constraint. In the third case, the first argument is false, so anything goes. So it's fine to have TT as a second argument and we return true. In the fourth case, if the first argument is true, well, it's not, it's false, so anything goes. There's no further constraint, so the second argument can be false and the constraint is still satisfied. So the one case where the implies constraint is not satisfied is the case where the first argument is true and the second argument is false. Okay. So I want to give you just a brief preview of how to think about the implies relation sort of at a higher level, other than just looking at it as this abstract set of return values. And you can pronounce implies in two different ways. You could say, for example, true implies true, or you can say if true, then true. So implies implements a kind of a condition check. If the first is true, then the second must be true. So here's a question. If I say, if it's raining outside, then the streets are wet. First off, how would you change that into an equivalent statement using the word implies? It's raining implies the streets are wet. If it's raining, then the streets are wet. It's raining implies the streets are wet. It says, if it's raining, if that's true, then it must be the case that the streets are wet. And given our usual interpretations of those English phrases, it's raining and the streets are wet, we would say that that implication is true. In most cases, okay, if there's a covering over the street, then it's not, but let's ignore those special cases, okay? If it's raining, then the streets are wet. Or you could say, it's raining implies that the streets are wet. And that implication is true. Okay. Now let's give an implication that's false. How about if 0 equals 0, then 1 equals 2? True or false? If 0 equals 0, well, that's true. Then 1 equals 2. Well, that's not true. So we have a case where the premise or the antecedent of the implication, if 0 equals 0, where that antecedent is true, but where the conclusion, 1 equals 2, is false. Now, in implies terminology, we would say 0 equals 0 implies 1 equals 2. And that's false, because the premise is true and yet the conclusion is false. So that implication as a statement in predicate logic is false. And later on we'll be able to well, it's false. Let's take another example. 1 equals 2 implies 3 equals 4. True or false? 1 equals 2 implies 3 equals 4. Well, the premise is false. 1 does not equal 2. The conclusion is 3 equals 4. That's not true either. So we have something that's false implies something that's false, and that is true. 1 equals 2 implies 3 equals 4. Okay? Because the premise is false, so it doesn't matter what you say in the conclusion. The overall implication is true. How about 1 equals 2 implies 0 equals 0? Here you have false implies true. Something that's false implies something that's true. Again, the premise is false, and so the overall implication is true. It's really, really, really important that you study this particular Boolean operator carefully because it's going to come back to haunt you when we get to predicate logic. It's really the hardest of the everyday logical operators to understand. It will be very confusing at first how something that's false can imply something that's false and that implication be true. But that's the way it is. And you can understand that by coming back to this algebraic definition of the operator, the implication operator, and it's just as it's written, and it implements this constraint. That only in the case where the first argument is true, must the second argument be true, and in all other cases, it doesn't matter. The constraint is satisfied, so you return true. Okay? Great. Good. Last idea. The last idea for this lecture. And the idea is that what we're essentially defining in these tables, think of these as tables with 3 columns. A column for the first argument, a column for the second argument, and a column for the return value, or the result of combining the elements in the first and second columns using the given operator. Let's go back and look at it in terms of the AND operation, the B AND operation here, right? If both input arguments are true, then the result is true. If the first is true and the second is false, then the return is false, and in all other cases, the return is false. We call a table of this form a truth table. These are called truth tables. And a truth table, which is typically written on paper, with columns and row lines and so on and so forth, is nothing other than a definition of a function, of a Boolean function. It explains how some Boolean function works, okay? It explains how some Boolean function works, what it does, okay? By systematically enumerating in each row the possible combinations of argument values, and then reflecting in the last column the result of the function applied to each, in this case, pair of input arguments. Okay, so a truth table for a binary function will have 3 columns, 2 argument columns and 1 result column. A truth table for a ternary Boolean function will have 4 columns, 1 for each of 3 input arguments, and then a column for the result. Now, if a function has 2 arguments, how many rows does it have? 4. Because there's 4 different ways of combining those 2 Boolean values. If a Boolean function has 3 arguments, how many rows will it have? How many cases are there to consider? 8. So to define a specific Boolean, ternary Boolean function, you have 8 cases. Therefore, you have 8 placeholders to fill in with Boolean values, and there's 256 ways to do that. Okay, so the arity of the function is 3. The number of cases is 8. And the number of different ways of returning values, the number of different patterns of return values, is 256. So that takes us back to this table here, where if the arity is 3, the number of cases is 8, and there are 256 different ways of filling in the return values, giving you a total of 256 different functions. And they would be indexed from 255 down to 0. Okay, and that gives you 256 total. Okay, so I lied before. That wasn't quite the last idea. The very last idea is, let's see if we can think about what the pattern is here. If the arity of a Boolean function is n, how many different cases will there be? How many rows will there be in the truth table? Okay, so if we were to come back up here, and so this is the number of arguments, this is the number of rows in a truth table, and this is the number of different truth tables that you can construct by filling in that last column in all possible ways systematically. Each truth table defines a function. How many functions are there? It's all the different ways you can fill in that template with a given number of cases. So I bet that you can see what the relation is between the first and second column here. If the arity is n, 0, 1, 2, or 3, for example, then the number of cases is 1, 2, 4, 8. And that leads to the very strong hypothesis that what? The number of cases is, well, it's 2 multiplied by itself, arity times. It's 2 to the n. That makes sense? Now the question for your homework is what goes right there. Okay, and that brings us to the end of the lecture. I do have some additional exercises for you to do, and very shortly, the next lecture will use the material that you've produced here in order to build up our first formal specification, our first implementation, if you will, our implementation for this class of the language of propositional logic. And if you master the material in this lecture, then the next one essentially combines this material with what you've learned previously about how to define syntax and semantics of a formal language, and it's just going to all fall into place. It's super cool. Okay, so stay tuned for a quick homework assignment on this material, and we'll be right back with the next lecture. Take care.